Uh, Good afternoon, everyone. Welcome back to session 2 of day 10 GATE 2021 online training program. Topic for today's second session is uh, fluid mechanics, to be presented by Professor Mahesh DP. Professor Mahesh DP is an associate professor in Department of Civil Engineering, Vidyavardhaka College of Engineering. Professor DP Mahesh has completed his BE in Civil Engineering from PES College of Engineering, Mandya, and he has completed MTech in Environmental Engineering from PES College of Engineering, Mandya. He has over 21 years of teaching as well as research experience, and his areas of interest are environmental engineering as well as fluid mechanics. So I welcome you, sir, for this session. Over to you, sir. Thank you.
Thank you, Avinash, for the nice introduction. And now I welcome all the GATE aspirants, and I wish you all the best for GATE 2021. And now I will going to give some points related to your GATE examination about the subject fluid mechanics and the hydraulic machines. Now, the topic to be presented is on fluid mechanics. And the fundamental before you understand the concept of fluid, one should understand the basic properties of the fluid. There are many properties of the fluids. The few important properties of fluids are displayed here. Mass density. The mass density, popularly called by the name density itself. What mass density and what is weight density, what is specific gravity and viscosity, specific volume, vapor pressure, and so on. So we have to understand the meaning of each term in detail before we proceed. These are all the various properties of the fluid. Now, let us understand the correct meaning of the mass density. Mass density is actually mass of the fluid to the volume of the fluid. For a given volume of the fluid, there has to be a known mass. And mass density, which is expressed in kg per cubic meter in the SI system. And its value is 1000 kg per cubic meter for water. Actually, as far as fluid is concerned, we commonly call the word fluid for both liquids and gases. So water is considered to be a standard liquid. So its value of density is 1000 kg per cubic meter. Similarly, weight density is another property of the fluid. Weight density we also call by the term specific weight. Weight density is the ratio of the weight of the fluid to the volume of the fluid. And it is expressed in the unit Newton per cubic meter in the SI system. And its value 9810 Newton per meter cube for water. Similarly, specific gravity. The most important property of the fluid is the specific gravity. Specific gravity is either the ratio of the weight density of the liquid to the weight density of water. Water is a standard liquid, and if you take the density of the liquid or density of the standard liquid, or even you can take weight density of the liquid to the weight density of the standard liquid, the numerator to be water, that value is 1000. And since if you wish to calculate the specific gravity for why the number 1 is for water, and one should remember at least these values for water. That's why I have shown the values of density, weight density, and the specific gravity for water, which is a standard liquid. Similarly, specific volume. Specific volume, which is exactly the reciprocal of the mass density. In the mass density, it is the ratio of the mass of the fluid to the volume of the fluid. Similarly, in the specific volume, it is the ratio of the volume of the fluid to the mass of the fluid. Now coming to the other property of the fluid, which is the most important property, that that is called viscosity. Viscosity, which is a property of the fluid which offers resistance to the movement of one layer of the fluid over another adjacent layer. You can see the figure. In the figure, you can see along y-axis, you can see this is the channel bed, and this will be the depth of the channel. And I have taken the two layers of the fluid. So the two layers of the fluid which are very close to each other. And they have a different velocities. The one layer has a velocity equals to u, which is very close to the channel bottom. The other one, which is slightly more, and its velocity is u plus du. There is a difference in the velocity, that is du, which is called relative velocity. And these two layers, which are adjacent to each other, they are apart by a distance dy. And they have a difference in the velocity is du. This is a very small change in the velocity, also called relative velocity. And because of and there is a liquid between these two layers which act as a lubricant for the flow. Thereby there is a resistance for the movement of the fluid. And the liquid which is in between the two layers, uh, that will cause some stress on these two layers. The upper will on the lower will on the upper layer. And the viscosity together with the relative velocity, which causes some certain amount of the stress on these two layers, so that there is a stress, and which is proportional to the ratio, the velocity gradient. The meaning of the velocity gradient is, here we have the difference in the velocity between the two adjacent layer, which is du, and the two layers which are very close to each other and apart by a distance dy. Then the ratio of the du by dy, which is called relative velocity, and the stress which acts between these two layers is directly proportional to that gradient value, which is called relative, the du by dy value. That is, tau is actually here's a symbol which is directly proportional to the velocity gradient du by dy. And that if you remove the constant of proportionality, so you will get a constant that is called mu, which is constant of proportionality, popularly called by the term viscosity of the liquid, or also called by the name dynamic viscosity. Similar to dynamic viscosity, we also have one more viscosity, that is called kinematic viscosity. And as far as viscosity is concerned, we have to distinguish the dynamic viscosity and the kinematic viscosity. Dynamic viscosity, most of the times we express in the outdated system, that is called CGS system, in the unit pies. Similarly, the kinematic viscosity, there is a system in we still use the CGS system, that we have to convert that into the present SI system carefully. The kinematic viscosity, by definition, it is the ratio of dynamic viscosity of the fluid to the density of the fluid. And it is expressed in Stokes and CGS system. The meaning of a Stoke, which is cm square per second, later we can convert that into meter square per second in the present SI system. Now coming to the types of the fluid. And before we understand the more on fluid, one should know that the various types of the fluid. The ideal fluid. What is ideal fluid? You can see the figure. So here along the y-axis, there is a velocity gradient, that is du by dy. Along the x-axis, there is a shear stress. And this classification is based on how the velocity gradient with respect to the shear stress. So the meaning of an ideal, you can look at this. This is an ideal fluid which is along x-axis. Similarly, ideal solid which is along y-axis. The other fluids which are in between these two, Newtonian, non-Newtonian, and ideal plastic fluid. Ideal fluid, which is an actually incompressible fluid and which has no viscosity, and it is an imaginary fluid. Ideal fluid, it is an imaginary fluid because in the real existence, no fluid which has no viscosity. So there is a fluid, any fluid which is in existence, they have got certain amount of the viscosity. They are called real fluids. Real fluid is one which possesses some amount of viscosity. Now coming to Newtonian fluid. Newtonian fluid is the fluid which obeys Newton's law of viscosity. The meaning of Newton's law of viscosity means the ratio of the shear stress which proportional to du by dy ratio. Any fluid which obey that the Newton's law, that means stress proportional to du by dy, they are called Newtonian fluid. That's why that curve which is a straight line, the curve which is straight line for the Newtonian fluid reason is the shear stress, which is directly proportional with the increase of this will also increase. Accordingly, we will have the straight line. In case of a non-Newtonian fluid, it is a fluid which do not obey in the sense which is not directly proportional. It can keep the value of the shear stress which increases with respect to the gradient to some point. After that, it will not obey. Such fluids are called Newtonian fluids. Similarly, ideal plastic fluid. Ideal plastic fluid is one which has a shear stress more than the yield value. And after that, the shear stress is proportional to the velocity gradient. You can look at the difference between the Newtonian fluid and the ideal plastic fluid. Though they look same, but Newtonian fluid which originates from the origin itself, whereas ideal fluid, plastic fluid, which has got some yield value. Now coming to one example based on the theory I have discussed so far. You can look at the example. If a 10 cubic meter of a mercury, which weighs 1360 kilonewton, calculate its specific weight. So there are four options. So which is the correct answer? So how to find the specific weight? Specific weight means weight density. So by definition, the weight density is the weight to volume ratio. Anyway, the weight of when I say density, please remember weight density is always the ratio of the weight to volume. The denominator is always fixed to value. That we always keep the denominator, the constant value of 1 cubic meter. When it comes to density, we always express both mass and weight per unit volume. Unit value means for each cubic meter, what is the corresponding weight or what is the corresponding mass. They are called weight density or mass density. Similarly, in the present problem, the volume of the mercury is given as 10 cubic meter. And out of the 10 cubic meter, its weight is 136 into 10 to the power 4 Newton. It is converted to Newton, thereby it is 136 into 10 to the power 4 Newton. So now, what is how to find the specific weight? Specific weight is the weight to volume ratio, because you have this much weight not in 1 cubic meter, which is in 10 cubic meter. If you divide by 10, automatically you will get the weight of the specific weight or weight density of the mercury, that is equals to 136 Newton per cubic meter. Per cubic meter is actually per cubic meter. Now another example. You can see another example. Calculate the specific gravity of a fluid which is having a viscosity of 0.05 poise and kinematic viscosity 0.035 Stokes. As I said earlier in the beginning presentation, I told you the viscosities are still expressed in the outdated system. You can see the kinematic viscosity is expressed in Stokes. The dynamic, when they say viscosity, it is always dynamic. It is 0.05 poise. So it is asked to find the specific gravity. So these are all the values. So we have to calculate the specific gravity. Dynamic viscosity is 0.05 poise. When it is in poise, we have to convert, poise means AGS unit, we have to convert that into the present SI unit. So how? Because each poise equals to 1 by 10 SI unit. 1 by 10 Newton second per square meter. When you divide the dynamic viscosity given in poise by 10, automatically that gets converted to SI unit, which is Newton meter per second square. So this is actually divided by 10. That corresponding unit in the SI will be Newton meter per second square. Similarly, for kinematic viscosity also, it is 0.035 Stokes. Each Stoke meaning is cm square per second. Each Stoke meaning is cm square per second. Then when it is cm square, it has to be converted into meter square. So each cm square will be equals to, because cm is nothing but 1 by 100 centimeter. So when you have cm square means 1 by 100 into 1 by 100, which becomes 1 by 10 to the power 4. When that comes to the numerator, it becomes 10 to the power minus 4. So that's why it is 10 to the power minus 4 meter square. 10 to the power minus 4 meter square stands cm square only. That's cm square per second, because cm square per second is called as Stoke. So this is how we can convert the dynamic and kinematic viscosity when they are given in CGS to a present SI. Only after converting them into the present SI system, we can able to calculate the specific gravity. Now, the kinematic viscosity, by definition, it is the ratio of the dynamic mu means dynamic viscosity by rho. Rho means density, the density of the fluid. So our aim is to find the specific gravity. We can able to calculate the specific gravity of any fluid provided if the density is known. So since both the kind viscosities are known in this equation, we can able to calculate the density of the fluid. So the density will becomes point when rho comes this side, when the rho goes that side, this is called nu. Nu is kinematic viscosity which comes here. So it will become finally 1428.5 kg per cubic meter. Density is expressed in the SI in kg per cubic meter. Once the density comes, we can calculate the specific gravity. Specific gravity, it is the ratio of the density of the fluid by the density of water. Density of the fluid, that is 1428.5. Density of water, which is standard value, density of water is always standard, which is 1000 unless specified. So this is D equals 1.428. Now you can see the out of the four option, there is one correct option, 1.41 for 2. So it is by A, it is actually, it should have been B, it should have been C, it should have D. So your correct answer is 1.428. Now coming to surface tension. So this is again the most important property of the fluid. So surface tension means it is a tensile force acting on the surface of the liquid which is in contact with the gas or on the surface between two immiscible liquid such that the contact surface behaves like a membrane under tension, which is expressed in Newton per meter. You can see the figure. In the figure, what we can understand here is, so these are the three molecules of the liquid. You are able to see the huge mass of the liquid. So these three spherical shapes indicates that the molecules of the liquid. The three different molecules are taken at the different places. One, the A, which is completely inside the liquid, the B and C, which are near the free surface. So the A is completely inside, while B and C, like ABC, you have numerous molecules of liquid. Now, what is actually happening to these molecules? The molecule A, which is surrounded completely by the surrounding molecules, so thereby there is a force of attraction on the molecule A in all the direction. So you can see this arrow indicating that this molecule A, which gets attracted by all the molecules from all the direction, so that the net force acting on the molecule A, which is 0, it is going to experience the resultant force 0. So thereby the molecule A, which is held in position, means that position of the molecule A will remain same unless affected by some external agency. Similarly, the molecules, the B is actually, which is situating near the free surface, then the C is, which is exactly at the free surface. And actually in case of molecule A, the force of attractions are gets balanced. So in the case of molecule A, since it is not completely inside, and the part of which it gets exposed, thereby the forces acting on the molecule B are not balanced, so that the molecule B is going to experience some downward resultant. Similarly, the molecule C, both B and C, since they are at the free surface, they tend to move in the downward direction because of the forces acting on these two molecule. They are more dominant in the downward direction. They pull these two molecules to go down, but still the free surface will not allow these two molecules to go down. The member, that free surface which acts as a membrane under tension, so that these two molecules will still in the same position. The force which acts at the free surface on these two molecules, which is not allowing these two molecules to go inside the liquid, that is called as surface tension. The surface tension is a tensile force which always acts away from the free surface. So there is a tensile force which always acts away from the free surface, which tries to keep the molecules which are at the free surface in the same position. This is the theory concept of the surface tension. So now, how we can have some case studies in the surface tension. So one among which is a liquid droplet. You can see the droplet is just like a droplet. You have seen droplet in the falls during rain. Several times you have seen. This is one such droplet. The droplet shape is spherical. So you can see the droplet which cuts into two halves like this. So what is this actually? So you're only seeing the one half of the droplet. So this edge of the droplet, this edge of the droplet which act as a free surface, hence there is a force, there is a force which is called a tensile force, called popularly called as a surface tension. So that at the same time there is some amount of the pressure, because unless it is just like that, when the air goes out of your vehicle tube, so then that the tube will not bulge. So the moment when you blow the air inside the tube, then it will bulge and it will get the shape. Similarly, the droplet has certain amount of life. So as long as that pressure inside and the force acting on the free surface, so they're equal and opposite, it has a life. When these two are not equal, then the droplet, it will lose its life. Similarly, this is called tensile force, the tensile force which acts away from the droplet. So here actually there is a pressure inside the droplet which tend to act in the opposite directions of the surface tension. For equilibrium, these two are equal. And finally, there is the pressure which is inside the droplet in case of the droplet, which is equals to 4. The final formula I have written, 4 sigma by d. The surf the liquid droplet which is always under the action of two forces. They are, one is a tensile force due to surface tension, because this edge length equals to circumference, which is pi d. The surface tension is denoted by the term sigma. Sigma into pi d is a tensile force which acts on this droplet, but it is away from the droplet. Similarly, this is the P. This is called pressure inside the droplet, and this is acting on the droplet on a projected area of the droplet equals to pi d square by 4. This force equals to P into pi d square by 4. This force equals to sigma into pi d. And for equilibrium, these two are equal and opposite. The moment when we equate these two forces, finally you will get this equation. So I am showing only the final equation for the pressure which is inside the droplet. 4 sigma by d is pressure inside the droplet. For curiosity, P is the pressure inside the droplet. Now, normally we feel that the pressure inside the droplet equals to 4 sigma by d. So seriously, which is not this value. The pressure inside the droplet in excess of outside pressure, which is equals to 4 sigma by d. Then what is the pressure inside? The pressure inside is always P for P plus the pressure outside. The outside pressure is called atmospheric pressure. The atmospheric pressure, because the pressure outside is atmospheric. The pressure inside, it should be more than the atmospheric, then only the shape you will get. That this droplet will have some shape. Similarly, then another case study for surface tension for hollow bubble. Hollow bubble and droplet, that liquid droplet, they are basically one and the same. This is the same figure I am showing. The reason is the droplet sometimes like a hollow the hollow bubble, particularly the soap bubble with hair, which has got two surfaces, just like the one is coated above the other. So when there are two surfaces, then this edge will get doubled. This gets doubled. Then pi d into 2 will be the free. Actually, I'm not showing there is a one more surface. There is a one more surface which covers this inner one. So thereby this edge, when you cut, you will get two length. Each length equals to pi d. Thereby total length is equal to 2 pi d, and that entire length of 2 pi d, that will be, then there is a pressure inside the droplet which is equals to P. When I say pressure, that there is a pressure force, corresponding force. That the force acting on the droplet in the opposite direction of this will be called pressure force, that is P into pi d square by 4. These two arrows, they are actually the forces. This is called a tensile force due to surface tension. This is called a pressure force. And these two are equal and opposite. And because of the droplet, hollow bubble is also a droplet, but which has two surface, a contact surface area. Thereby, this formula gets doubled of the previous one. Previous is 4 sigma by d, because it's a droplet which has only one free surface. In case of hollow bubble, and there is an adjacent to this, there is another bubble you have seen during washing clothes. So there is a film of a droplet which gets coated with another layer. So that's why it is 8 sigma, because same derivation, it's 8 sigma by d. Now coming to the liquid jet, it is a liquid jet. Actually, this is a specimen of the liquid jet. You can see, able to see the length of this is a specimen jet. Its length is L, the diameter is d. So when you cut this, you will get this shape. When you cut this, you will get this shape. So this arrow indicating the surface tension. So arrow indicating surface tension. Let it be sigma. So let it be sigma. So surface tension, then the each edge will be called as free surface. Then L plus L become 2L. Then sigma into 2L will be the tensile force due to surface tension. So there is a pressure inside the liquid jet. This will act in the opposite direction on the area. When you view from this angle, that jet will looks like a rectangle having the dimension which is equals to L into D. This edge will looks like a D. This length will look like L. It is a projected area of the liquid jet will be rectangle. Its area will become L into D. Then pressure will be P. Then pressure force will be P into L into D. Then for equilibrium, the tensile force due to surface tension, which equals to sigma into 2L. So that there is another force called pressure force. The pressure force, which is also called as a bursting force, that equals to P into L into D. The moment when you equate, the finally you will get. Only thing is, for problem purpose, you must remember the two formula for pressure. One for droplet, which is 4 sigma by D. For liquid jet, it will be 2 sigma by D. For hollow bubble like soap bubble, it will be 8 sigma by D. These are so by in the numerical problem we can calculate diameter, we can calculate surface tension or anything. Sometimes for curiosity they will ask you to find what is the pressure inside the droplet. The pressure inside the droplet, please remember that P is actually the pressure inside the droplet in excess outside. But for example, imagine there is a droplet. The pressure found for the droplet using this formula, say 2 Newton per cm square, which doesn't mean that the pressure inside the droplet is 2 Newton per cm square, because a 2 Newton per cm square is the excess pressure when compared to the outside pressure of the droplet. Then actually the pressure inside, the pressure outside the droplet, if it is 10, the inside found using this formula, if it is 2, then the pressure inside the droplet is 12. The pressure inside the droplet is 12. Similarly, so now there is another property. This is also most important property as far as fluid properties are concerned. It is called capillarity. Capillarity is the phenomenon of rise or fall of a liquid in the glass tube. It's just a small glass tube which normally held vertically in a liquid like this. You can able to see the figure depicts the capillarity. The capillarity is just a rise or a fall of a liquid. You can see just a glass tube. It's a very small glass tube that is held vertical in a container like this. So the moment when you hold the glass tube like this, the liquid gets an entry through this. The liquid rises in the glass tube, which depends on several factors. The factors on which the amount of the liquid which rises in the glass tube are: one is surface tension, the one more is density of the fluid, the one more is diameter of the glass tube. So these are all the factors on which this amount of the rise or even fall depends. So now we have this formula. Just I am showing the final formula for capillary. This H is actually this is the outside general level of the liquid in the container. So you can see the same liquid when you hold the glass tube, which gets raised above this level. This height will be called as capillary rise, which can be found using the formula 4 sigma cos theta by rho GD. What is sigma? Sigma is already known to you. Again, there is a free liquid surface inside the glass tube for the same liquid. The liquid when goes inside the glass tube, which has a free surface, and at every free surface there must be a force called surface tension. Why this force is so inclined? The reason behind this, the liquid when inside the glass tube, which has got certain meniscus, thereby tangential to the meniscus, when you show the surface a tensile force which looks like an inclined force and which has certain amount of inclination called theta. That is also called as contact angle. It is the contact angle between the glass tube and the water. And the rho is the density, D is the diameter. If you know theta value, surface tension value, and the diameter of the glass tube, we can able to find the H called capillary rise. And surface tension is always expressed, since surface tension is a force, that's why its unit is Newton, but it is always expressed per unit length, that's why its unit is Newton per meter. Similarly, theta is the contact angle, rho is the density, D is the diameter of the glass tube. So now coming to capillary fall. The interesting thing in the capillarity is whether it is a capillary rise or a capillary fall, the equation to be same. The equation to be same, but even the figure gets reversed. But even the figure gets reversed, so you can see, imagine this is a mercury. I told you to look for mercury. Say in the previous case, it was a water. So when it is mercury, the liquid which gets inside, and it can only raise this amount, leaving this up. There is a space from this level to this level, and this is called depression. This is called depression. That is expressed as I, depression or even fall. So now, when you again every time for a capillarity, there are two forces. There are two forces. Actually, why the liquid inside the glass tube which gets balanced? The reason behind this is very interesting. There is a force which acts on the free surface of the liquid which is inside the glass tube, that is called tensile force. We can find its vertical component. We can find it, you can see it's acting on the glass but not vertical. So we can find the vertical component of this force to act on the water which is inside the glass tube for height equals to h. That value will become sigma into pi d, because sigma is actually tensile force. When that is converted into vertical component, it will become sigma pi d. Sigma pi d. So then the liquid inside the glass tube having height h, its weight will becomes, because the weight of any liquid we can calculate provided when the volume of the liquid is known. So the rho g, called weight density, multiplied by the volume of the liquid inside the glass tube for a height h, that is pi by 4 d square is the cross section, h is the height, you will get volume, multiply by weight density, that is called rho g, you will get the weight of the water, which acts downward, the vertical component of the tensile force which acts upward. The moment when you equate, because as long as these two are equal, this gets balanced, this remains constant. With the moment when you equate these two, this is the final equation you will get. This is the final equation you will get. Because in the gate examination, they will not ask you to derive any of the equation. Instead, you should remember the equation using which we can solve some numerical problems. Only thing is, you have to remember the equation. You have to convert some parameters to the required unit. Similarly, capillary fall. As I said, capillary fall, capillary rise, both have the same formula. Both have the same formula, because the two forces which are acting on the liquid which is inside the glass tube, they remain same in either both the cases. Thereby, the formula remains same. This is called H. Everything is same. Only the contact angle in case of water means capillary rise. It will be 0 degree. That water gets raised in only when the liquid is water. Water gets depressed only when the liquid is heavy like mercury. The theta is the contact angle which is 0 for water and which is nearly 130 degree for a mercury. Now we have, based on this theory background, let us have one simple numerical problem. So this problem, normally they has problem like this. The capillary rise in the glass tube is not to exceed 0.2 millimeter of water. Capillary rise is given in the glass tube, which is not to exceed means it is restricted to 0.2 mm. Means it will rise by that much. Determine the minimum size. Minimum size means the size of the glass tube. Normally when it comes to size, you are finding diameter. Given that the surface tension for water in contact with air has 0.0725 Newton per meter. So these are all the various options. So which is the correct answer? You have to do the exercise like this. So the capillary rise is given, which is 0.2. Since it is given in mm, which should be converted into meter. That's why 10 power minus. When you divide by mm by 1000, it gets converted to meter. Similarly, surface tension. That is 0.02725 Newton per meter. 0.0725 Newton is the correct unit. So contact angle theta, though it is not given, since the liquid is water, it is by default 0 degree for water. Sometimes this value is also specified for water, we have to use. Unless otherwise specified, we have to use theta as 0 degree for water. We have to use 0 degree for water. When it is specified like 1 degree, 2 degree, even though it is water, we have to use a specified value. Then capillary rise, the moment when you substitute the given values in the formula, you will get the H value, D value. So when you, because H is given, which is 0.2, which is, this value is 0.2. So D is the only, that is called size of the glass tube. We can calculate the diameter. You will get the value in meter first, which can be converted, because the option given in centimeter, you can convert this into a centimeter, which become 14.8 cm. Now the correct answer is B. So this is how we can calculate the capillary is the diameter of the glass tube. Let us have one more example. So a glass tube of 4 diameter is immersed in water of surface tension. The contact angle what will be the capillary effect in millimeter? So it looks similar to the previous problem. The diameter of the glass tube is 4 means 4 into 10 power minus 3 meter. Then surface tension is 0.0075 Newton per meter. Since it is water, you can see the contact angle is given. Even though it is not given, we normally take 0 degree. Then capillary rise, the formula for capillary rise or actually while solving either it is a capillary rise or a capillary fall, so you will come to know only at the end by looking at the sign. So sometimes when liquid is not specified, you will come to know that whether it is a rise or a fall. So when you substitute, you will get the H value called capillary value, that is 0.76. The sign is a plus, which indicates that it is a rise. Now your answer is D. That the fourth answer 0.76 m. Actually, you have one more 0.76, but it is a fall actually. The answer, but why do you say? How do you say that this is a rise? Because we are getting sign positive. That's why it is called rise. When the sign is a negative, it is actually a fall. So when for a liquid like mercury, you will get negative sign. That indicates that there is a fall of liquid. Since the sign is positive, so it is actually rise. Your answer is 0.76 rise. Now coming to the pressure and its measurement. So before we understand the fluid statics, we have to know the correct meaning of pressure, and there are certain laws in the pressure measurement. Basically, the pressure means it is the ratio of the some force to certain area. So if you just imagine inside the liquid, a film of a liquid in the form of an area, a very small area. Say just imagine inside the liquid an area, a very small area. The liquid which surrounds to that area, it is assumed to act normally on it. That force which is going to act on that imaginary area of the liquid, that will be called df. Then that df it is an assumption that it will be act on an imaginary area dA normally. So if you increase dA to capital A, means when the area expanded to A, then df will become f. Then the intensity of the pressure will always equals to, there is a force pressure, a force by the area. So pressure is always expressed in the unit Newton per square meter in the SI system. So there are two popular laws as far as pressure is concerned. One is called Pascal law. One is called Pascal law. The Pascal law, which is a very popular law, which is applicable for a fluid at rest. Whenever the fluid is at rest, so you just imagine when the fluid is rest, any portion of the fluid you just imagine. So the fluid, there are several fluid particles which is acting simultaneously from all the direction on an elementary fluid which is completely inside the liquid which is at rest. Which the intensity of the pressure which is acting on an imaginary fluid inside will be equal in any direction. That is called Pascal law. That's why it is Px, Py, Pz. Px, Py, Pz are the pressure intensities in all the x direction, y direction, z directions, in any direction. It's not only from in these three directions. In any direction, they are equal. That's called Pascal law. And using why this law, this law is so important in understanding how the manometer works, because the manometer, they have designed the manometer in order to calculate the pressure. Simply, when in the industry there is a pipeline. There is a pipeline. It can carry a water, it can carry an oil, or it can carry any liquid. So with an enormous amount of pressure. So if you wish to calculate the pressure of such huge pipes, so we can just fix a gauge, because normally gauges are designed to work to give the pressure, and the principle behind this is Pascal law, and there is another law called hydrostatic law. Now coming to the another law, that is hydrostatic law. So in the hydrostatic law, the statement of which is there is a rate of increase of pressure in the vertical downward direction, which must be equal to the specific weight of the fluid at that point, which means that you just imagine a liquid surface. As you go below the liquid surface, the pressure keeps on increasing. The pressure keeps on increasing at any point inside the liquid. Then the rate of increase of pressure in the vertical direction, which always equals to specific weight, that is del P by del rho, will be equals to GH, or simply P equals rho GH. Now with this background, we have one simple problem. You can see this is a very simple problem. Calculate the pressure due to a column. Column means height. Column of 0.3 meter of water if the density of water is 1000 kg per cubic meter. So the problem is there is a liquid, so say that is a water, which has height equals to 0.3 meter from the free surface. From the free surface. What is the pressure at a point which is 3.3 meter below the free surface? Normally, we assume the free surface means where the pressure is atmospheric, we normally do not consider. We do not consider means we neglect the pressure which acts at the free surface because it is an atmospheric pressure. So we keep measuring or we start measuring the pressure in any liquid from the free surface, considering free surface as a reference where the pressure is taken as a zero. So now the column of water is 0.3. Then pressure intensity, there is a formula, P equals rho G. This is hydrostatic formula. At any point in any liquid, at any depth, we can find pressure, provided if the density of that liquid is known and the point where you wish to find the pressure is known using this formula. This is called rho GH because manometers are designed to work on this principle only. Rho, since it is water, rho is 1000 and the height by which that point where you are finding the pressure below the free surface is 0.3, then finally the pressure inside will be equal to this much. Then your answer is P. Actually, you will get the pressure answer, your pressure answer in Newton. In all the problem, when you substitute every value in Newton, in SI, you will get the SI unit of all the parameter. The SI unit of P is Newton per square meter. When that is converted to cm square, Newton per cm square, you will get this answer. You always see in which unit the answers are given. In which unit the answer is given. You must convert the resulting value at the end to the required unit. So because pressure sometimes it will be Newton per cm square, it will be Newton per meter square, it will be Newton per mm square. So we have to convert at the end the pressure which is calculated in Newton per meter square to Newton per cm square. Now, coming to types of pressure. This is the most important as far as design of the gauges are concerned. So now types of pressure. There are various pressure types. We know gauge pressure, vacuum pressure, atmospheric pressure, absolute pressure. Actually, there are two systems in which we measure pressure. The two systems to measure the pressure are, one is called absolute pressure system or complete vacuum. The other one is called atmospheric system. You can see in the figure, you can see in the figures, you can see the bottom one is called absolute zero pressure or complete vacuum. In the middle, the horizontal line which indicates that atmospheric pressure. The middle horizontal line which indicates that atmospheric pressure. And the moment when you measure the pressure using atmospheric pressure as a reference, there will be two values of pressure. Atmosphere, anything you measure above the atmosphere in the sense keeping atmospheric pressure as a reference. For example, if you want to measure the pressure using atmospheric pressure as zero, which means that anything above zero, that is called gauge. If you want to measure the pressure using atmospheric, anything below zero, which is called vacuum. At the same time, atmospheric pressure is not a zero, but it is we actually taken as zero. We assume that as a zero. Atmospheric pressure we rounded to zero and we measure the pressure, and above the atmosphere it will be called gauge, below the atmosphere it will be called gauge. Normally the gauges, pressure gauges in the laboratory or in the industry, they are designed to work on this principle. Gauge pressure is one which is above the atmospheric value. Vacuum pressure is one which is below the atmospheric value. That's why you can see the point is which is above the atmosphere. This is actually not atmosphere. It is atmospheric value. It is atmospheric value. The point A having pressure which is more than the atmosphere. From here is a complete zero means the reference line. It is a vacuum. So from here to here, you say you have 10. So anything more than 10, this is called above the atmosphere. Anything below 10, which is called below the atmospheric value. So that's why this one is called gauge, this one is called vacuum. For example, atmospheric is 10, imagine in any unit 10. So this value, the vacuum pressure is not at 10, it is still less than 10. This pressure is gauge pressure, when atmospheric pressure is 10, the real pressure is more than 10. But since we measure from this level, it is actually maybe 10, 5 or 6. Anything above the atmospheric you are measuring, that's why it is called gauge, without considering the atmospheric value. Atmospheric value means this much pressure. Similarly, absolute pressure. Absolute pressure means irrespective of the pressure value, when the pressure is measured from the complete vacuum or absolute zero, they are called absolute pressure. Absolute pressure is one which is always measured from the complete vacuum. Absolute pressure means a real pressure, which is always measured from the complete vacuum. Now coming to manometer, there are many manometers. So basically we have two types: simple manometer and differential manometer. In the simplest form of simple manometer is called piezometer. You don't find this, the simpler than this manometer among simple manometer. The simplest form of the simple manometer. You can see the figure at the right end. So that circular one indicating that pipe which carries a fluid under pressure. That center point is A. And normally we measure the pressure at the center. That's why it is called P, the pressure center. And this is the pipe actually. You can see the cross section of the pipe. So how to find the pressure using this glass tube which bends right angle, which is called piezometer. It's a right angle bent glass tube fitted to a pipe at any point where the pressure is to be measured. So what happened? The moment when this is called piezometer. So when the moment actually piezometer is fitted with a valve. The moment when the valve, if you want to know the pressure, you open the valve. Then liquid inside going in the pipe with the pressure that gets rushed into the tube. It will, and the amount by which it rises in the tube, which depends upon the pressure value inside the pipe. If the pressure is less, it will not rise so much. If the pressure is more, it will rise more. It will rise more. Accordingly, we can find the pressure inside the pipe using the formula P equals rho G. If we just know the height by which the liquid rises, actually this is called piezometer, which has a graduation with a starting value 0 with respect to the pipe center. We record the H value with respect to the pipe center only. So using this formula, we can find the piezometer. Similarly, we have another type of simple manometer, which is called U-tube manometer. So U-tube manometer, when you use, why? Because the tube which is in the form of a letter U, that's why it is called U-tube manometer. So you can see there are two figures, one for gauge pressure, the other one for vacuum pressure. What is the meaning of gauge pressure? Sometimes the pipe carrying a fluid which has a pressure more than atmosphere. There are cases where the pipe carrying fluid under which is less than atmospheric value. So whenever the pipes are carrying a liquid under a gauge pressure, so the first figure we refer. So how do we say that the pressure inside the pipe is a gauge or a vacuum? Just if you connect the manometer to the pipe, like in the first figure means figure A. First figure. So the moment when the valve is opened, the liquid inside the manometer is already a reference liquid, also called as manometric liquid. We normally practice with mercury. The shaded one inside the mercury, inside the manometer is a mercury. So the moment when the valve is opened, the liquid in the pipe will try to push the mercury. The moment when the mercury which goes down, the corresponding rise can be seen in the other side of the U-tube. So you can see the liquid in the U-tube which gets raised. So which indicate that the pressure inside the pipe, it has a capacity to push the mercury. It has a capacity to, the other side is, since the other side of the U-tube is always kept open, means the other side, the mercury which is under action of air. So the left side of the mercury which is under the action of the liquid which is inside. When compared to the air acting on the mercury in the right side, the liquid which is inside the pipe which is acting on the mercury is dominant, because you can see the rise of mercury in the other side, that exhibit that the pressure acting on the mercury in the right side is a weak compared to the pressure inside the pipe. That's why it is called the pressure inside the pipe is called gauge. The moment when you get these variations in the mercury in the manometer, and finally it will show some variation and it comes to rest. As long as the pressure is constant, this figure, the difference shown by the mercury in the manometer is constant. So then we will record some height like H1, H2. So using this, we can find the pressure. Actually, PA, what is PA? It is the pressure inside the pipe. Whether it is a gauge or a vacuum, only thing is you have to find the pressure inside. So how this formula, that is PA plus, actually we always consider one reference line like this. This is called datum line. This is called datum line. So this datum line, so the moment when the valve is open, when the valve is open, the liquid rises here. Pa means the pressure inside the pipe. Rho gh. What is rho gh? It is actually density of the liquid in the pipe. That h is the height of the liquid. You can see in the left side there is a, this is called datum line. This is called datum line. Please remember. This is called datum. Rho 1 g into h1. That rho 1 g1 to h1 means it is the density of the density of the liquid in the U-tube. So this is rho 1 g into h1. So rho 2 g into h2 means you have mercury in the other side limb. According to the Pascal law, so the pressure intensity will remains equal. So for a given datum surface, that is h rho 2 g into h2. This is actually rho pressure inside rho gh. So the moment when liquid goes like this, so we can find even this figure is not a constant. So we can consider the datum line even through this line. Datum line, it is up to us to select. And when the datum line is taken, please ensure that it's a general equation. So when the datum line is written, ensure that the difference in the mercury level can be taken. So this datum line, instead of writing here, you can take somewhere here, which for such a case, it will become rho gh PA plus, the other side will be this much height. So since it is a general figure, so using this, we can find the pressure inside the pipe. Similarly, for the pressure, for gauge pressure. So for gauge pressure, so just if you look the level of mercury whether the pressure inside the pipe is a gauge or a vacuum. In this case, you can see the mercury level in right side compared to left side is more. There is a gauge pressure. In this case, the mercury level in the other side will be the moment when you connect the water, say liquid which enters here and will try to act. But since the pressure, the other side is open to air, the air will act, that the air will be dominant compared to the liquid inside the pipe. Which means that the pressure of the liquid which is inside the pipe, which is less than the atmospheric value. That's why it is called gauge. So we draw the horizontal line here. Actually, this line, instead of writing here, it should have been, it is better to write here. So that it is PA plus rho into G into H. So imagine this height is H plus rho into G into H of this liquid. So by equating this, we can calculate. So this is how we can calculate the pressure. Actually, we consider the datum line only at the point where such that the mercury difference can be recorded. The purpose of considering datum line, so datum line is always a perfectly horizontal line. It can be either at this level for gauge or at this level for vacuum, because above this level you have the difference in the mercury. Now coming to a problem pertaining to manometer. You have a pipe contains oil of specific gravity 0.9. A differential manometer connected at the 2 points A and B, which shows a difference in the mercury level, has 15 centimeters. When I say manometer, so we also have a differential manometer. Differential manometer is again a U-tube manometer, but both the end of which we always connect to two pipes or to two different pipes in the same pipe. So the U-tube is, manometer is just a U-tube which contains some liquid inside. Its ends are always connected to the pipe in order to measure the pressure at those points. So they works on the principle of Pascal law and as well hydrostatic law. So now in this problem, there is a pipe containing oil having specific gravity 0.9. A differential manometer connected at the 2 points A and B, which shows a difference in the mercury level as 15 centimeter. Calculate the difference of pressure at the 2 points. These are all the values are given. But one thing you please remember, whenever a differential manometer is connected at the 2 points A and B in a given pipe, A and B are the 2 points of the same pipe which carries oil of specific gravity 0.9. If that is the case, please remember, just if you know the mercury difference without knowing how above or how below the liquid in the pipe inside the glass tube, that is not required at all. If you know just the mercury difference, the difference in the mercury in the manometer, which is enough to calculate the pressure difference between the 2 points when the differential manometer is used. So ensure that the differential manometer is connected to different points in a single pipe or in the common pipe. When differential manometer is connected to two different points in the two different pipes carrying two different liquids, they may kept at same level or at different level. So you cannot use this concept. So this formula can be used. So now only when the differential manometer is connected to 2 points in the same pipe, because it's a single pipe, it's a single pipe. So the 2 points are connected by the differential manometer, and the manometer showing difference 15 centimeter. Thereby we can calculate. Now let us see the specific gravity of the oil is 0.9. The difference in the mercury level is 0.15. Then specific gravity of the mercury is 13.6, though it is not given, it is a standard value. The density of the oil, we can calculate the density of any liquid provided its specific gravity is known. So that is 0.9 into 1000, 900 kg per cubic meter. Similarly, density of mercury. We have to ready with these values because at the end we have to substitute. Density of mercury is rho suffix g, which is 13.6. Density means it is always specific gravity of that liquid into 1000, which is standard liquid. So now the pressure difference between the 2 points A and B is given by, this is the formula, this is the ready formula in order to calculate the pressure difference between the 2 points only when differential manometer is connected to two different points in the given pipe or the single pipe. That formula is G into H, rho suffix G minus rho 1. What is H? It is a mercury difference. What is rho G? It is the density of the mercury. Because the manometer has a mercury, its density is rho G. Then what is rho 1? That rho 1 is the density of the liquid which is in the pipe. That is oil density. So when you substitute everything, you will get the value of the pressure. It is actually not the pressure neither at A nor at B. This is the pressure between those 2 points. Please remember, this formula will give only the pressure difference. Differential manometer is meant to give the pressure difference. It's not to for the pressure at A or for the pressure at B. By knowing the difference of the pressure between any 2 points, we can also find the pressure at either at A point or B point by knowing the pressure at least in one of the point. So 18688 Newton per meter square is the answer. Then your answer is B. Now coming to hydrostatics. Actually, when you say hydrostatics or fluid statics, that means when the fluid is at rest. While I was explaining viscosity in the very beginning slides, there is a relative velocity between the two adjacent layers. When the fluid is taking, when there is a movement of the fluid, each layer of the fluid will going to experience certain amount of the shear. But in case of hydrostatics, since it is at rest, there will be no relative motion between the two adjacent or neighboring fluid layers because it is completely at rest. Thereby, the value of du, which is 0. Because of that, the velocity gradient, it builds 0. So because of du by dy 0, the shear stress which is equals to mu into du by dy formula, that value is also, this is actually mu into du by dy. It's not du in the denominator, it is dy, which is 0. So since shear stress is 0, thereby, then what are the forces acting on the fluid fluid particle? The forces acting on the fluid particle are it can be a pressure force of the fluid which is assumed to be normal to the surface, or even can be the gravitational force, gravity force, which is nothing but its own weight. Now, vertical, there are several cases when imagine when there is some portion of a body which is immersed, so that is exposed to the liquid. Imagine there is something when you submerge inside, so the liquid will have direct contact with the submerged portion, that for even though the liquid is at rest, so it tends to act on that portion. So that is it is an assumption it is going to act on the submerged part of the body normally. So whether the force is same when it is submerged inclined, when it is submerged vertical, when it is submerged horizontal. So there are a different. It all depends upon the way in which the body is submerged inside. So first, let us consider when the plane area or plane surface submerged vertically. This figure depicts, so this is just an episode shape. So this is an area of the submerged part which is completely inside the liquid, but it is submerged vertical. It is that is a AB is a plane surface. It is submerged vertical. So the figure you can see here. So now what is going to happen, because it is completely inside the liquid surround this figure and this figure one and the same. This how it is submerged vertical. So what is the shape of this? You can see this. What is the shape of this? Now we to calculate the forces acting on the submerged portion. So this is the formula. This is the total formula. I'm showing direct formula in order to calculate the total pressure. Doesn't mean that it is a pressure. It is actually a force. Total pressure is actually a force acting on and acting on this submerged part when it is submerged vertically, and the G is the center of the submerged part. Center of the submerged part. P is the point which is slightly below the G where the force F will act. The F is called actually a total pressure. So that will act at the point P. It always act below the point G. We can prove that F will act, and that value equals to rho G AH bar. What is rho? It is the density of the liquid in which the body is submerged. What is A? It is the area of the plane area submerged. What is H bar? It is the center by which it is the height by which the center of the submerged portion. This center is here. You always measure from the free liquid surface. That is called as H bar. And friends, please remember, as far as numerical problem are concerned, this formula plays a vital role. Vital role. Only thing is, what is the area and how below the center is and in which liquid is submerged. That's all. If you know these three parameters, we can able to find the force. Rho means the liquid density. A means the area. But sometimes the area is rectangular, sometimes it's a triangular, even circular. So accordingly we can calculate. The H bar is sometimes the center of the plane area will not be given direct. So that we have to find out. Similarly, what is center of pressure? Center of total pressure is nothing but the total is actually a force of the liquid acting normally on any submerged part. Whereas center of pressure, which is total pressure and center of pressure, these two are not the pressures. The first one is the force, the second one is the distance. What is the center of pressure? It is the height by which this force will act on this when you measure from the free liquid surface. When you measure from the free liquid surface, this is the point of application of this force which acts normally. This I am showing here, which you can see on the AB there is a force F which is exactly acting at the point P. And using this formula, we can able to find even the point where this will be acting. Ig means center of a gravity. Sorry, it is a moment of inertia. It is not Ig, it is I suffix G. It is a moment of inertia of the submerged body about an axis passing through a center parallel to free surface. The formula is very interesting. Ig, I suffix G is actually, I suffix G, it is the moment of inertia of the submerged body about an axis passing through the center parallel to water surface. So that formula you have to remember depending on the geometrical section. Then AH bar plus H, it's also AH bar plus H bar. H bar is, it is the center distance from the free surface. If you know Ig, if you know H bar, we can able to find out both. Similarly, we also have the one more case that is called inclined case. Whether it is a vertical case or an inclined case, or a vertical case, for finding total pressure, the formula remains same. F equals rho A J A H bar. For total pressure only the formula is same. Rho G A H bar. Only thing is you can see the figure. It is actually this is the actually inclined plane surface. So you can see the inclined, that area you can see, but it is inclined by an angle theta. Actually the center when you measure from the free surface, it is called H bar. You have to measure carefully using some trigonometry background. So you have to calculate this. So for finding center of pressure, formula is Ig by H bar sin square theta plus H bar. Now with this background, we have a simple problem. Calculate the total pressure on the circular plate of diameter 1.5 meter, which is immersed vertically in water in such a way that the center of the plate is 3 meters below the free surface of water. So now here you have a circular plate which is submerged vertical at a distance equals to 3 meter. So at a distance equals 3. We have to find the area, and then H bar is directly given in the problem. Just substitute in the formula rho G H bar. H bar is given in the problem itself. A diameter is known, you can find A. Then F equals rho G H bar. When you substitute, you will get F 52002.81. Your second answer is the correct answer. Only thing is you have to carefully calculate both area and use the formula correctly. Then we also have one more problem. This is still interesting problem. A tank contains water up to a height of 0.5 meter above the base. An immiscible liquid of specific gravity is filled on the top of the water up to a height equals to 1 meter. Calculate the total pressure on one side of the tank. Take the width of the tank as 2 meter. So now you can see there is a tank here. So in the tank we have two liquid. Below we have water for a height equals to 0.5. Above we have oil for a height equals to 1 meter. And we have two liquids. When the two liquids are taken in the same container and these two liquids are always get separated, there is a layer called immiscible layer which separates the two liquids. The lighter one will be above, the denser one will be below. So since water is a denser, you can see like this. What is this figure? This figure is called pressure distribution diagram. We can find what above oil we have air. So then the pressure start from this point called A. The pressure at A is 0. Atmospheric pressure we don't. Then pressure at D we found here. Using the height of oil, that is rho GH. You can find the pressure at any point in any liquid at any depth. So at A, the pressure is 0. It is at D, the pressure is rho GH, 800 into 9.8. At bottom of the tank, with the pressure is the pressure at D point plus pressure due to water. That is the most important. The pressure at D point plus pressure due to water. That will be the pressure at the bottom. After finding the pressure at D point and at the bottom, we can draw this figure. We can able to draw the pressure distribution figure. In the pressure distribution figure, you can see the pressure distribution figure. So what we have to do is you have to construct one triangle indicating the pressure at D point equals to 7848. You can see the pressure at D point, and actually the horizontal ordinate in this diagram will indicate the pressure starting from point A to point B, means point A. So pressure keeps on increasing from top to the bottom. The pressure at A is 0, pressure at D will be this much, pressure at bottom will be this much. So now, so we draw an horizontal line through this point. It means that this is the pressure at D, this will be the same pressure, and the remaining, the pressure at the bottom will be 4905. Once you write this diagram correctly, this is the pressure at D. Accordingly, you draw horizontal line. Then what to do? Then what is the pressure at the bottom? That is the pressure at the bottom, which means that 7848 plus 4905. That's why it is written. Then draw horizontal line. You will get three different shapes: triangle, triangle, and rectangle. Then it is an assumption that in the triangle, the force F1, F2, F3, in this diagram, there are three forces acting F1, F2, F3 at their respective centers. So to find them, we have to use, then for example, force 1. It is the area of the triangle into width of the tank. The tank has got width equals to 2 meter. It is given in the problem. Area of the triangle, which means that the base is actually not the side, which is actually pressure value. The height is only the height of the liquid. So if you just calculate the area of the triangle, that is half into base into height, multiplied by the tank width, so you will get the force 1. Similarly, force 2, then area of this rectangular portion multiplied by the width of the tank, which is common for all the three. So that is called 2 meter. Then similarly, F3. After drawing the pressure distribution diagram, we can be able to calculate F1, F2, F3. These are the three forces acting on the respective centers. By using the formula, area of the figure into width of the tank. Area of the figure into width of the tank. Area of the figure means area of that particular section. So then when you add all the three, you will get the total pressure which acts on the tank in any of the vertical side. That answer finally is 18148.5. So your answer is C. 18148. You have to draw this figure, and you also draw this diagram. So in order to calculate the total pressure on any one of the vertical side. Similarly, in this problem, a circular plate of 3 meter dia, which is immersed in water in such a way that its greatest and the least depths below the surface are 4 meter and 1.5 meter respectively. So now it is not specified how it is immersed, but the moment when you see the data, we will come to know that it is kept submerged inclined. How? Because it has a diameter only 3. It has a diameter only 3. When it is immersed vertical, you remember, when it is immersed vertical, for example, it is immersed vertical such that the greatest and the least depths means, greatest means the upper edge from the lower edge from the free surface. Least means the upper edge from the free surface. Since the upper edge is 1.5 meter and the lower edge is 4 meter, When it is when it is submerged vertical, the lower end should have been, it is 1.5 plus 3 4.5, but still it is only 4, means unless you incline, you cannot get 4 meter as the depth for the lower edge. So by looking at the data, you will come to know that how it is submerged. So accordingly we write the figure. So we write the figure such that, so actually this figure is only for reference. Originally the figure is here. So this is the circular plate kept submerged inclined. So this edge will be 1.5, this edge will be 4.5, sorry, 4. So now, so this is the center of the plate. We have to find this. So this is theta. We have to find this. This is theta, means this is also theta. You can see in the triangle, we can find the theta using the formula. The area, as usual, area of the plate, pi d square by 4. Sin theta, you can find easily, that is opposite side by hypotenuse, sorry, adjacent side by hypotenuse. So we can find sin theta. So before you calculate the total pressure, you must find the height by which center is below. That is this FG height you are supposed to find. For FG height, please remember, FG is actually sum of 1.5 plus. So the 1 bg set times of sine theta. So when that is added, you will get h bar. Once h bar comes, you will get total pressure. That is rho g ah bar. So even though it is inclined, the formula for total pressure that will remain same, which is rho g ah bar. Similarly, for fluid kinematics is a branch of science which deals with the motion of the particles without considering the forces causing the motion. In the fluid dynamics, we will consider. So here we do not consider. Then the methods of the fluid motion. You can see there are two, basically Lagrangian method and the Eulerian method are the types of fluid motion. Now coming to types of fluid flow. So laminar and steady and unsteady flow. Steady flow is when everybody knows the steady flow, where the fluid characteristics like velocity, discharge, density, at any point they do not change with respect to the time. With respect to the time. In case of unsteady, they keeps on changing. So similarly, laminar flow and turbulent flow. Laminar flow means in which the fluid particle will move along a well-defined paths, or nothing but in a streamline. And all the streamline, they are parallel and straight also as well. So whereas a turbulent flow, and they are not straight and parallel, and instead they are very jog. Rotation means, and rotation flow and rotation means that fluid particle, they keeps on rotating about their axis. Uniform and non-uniform flow. Uniform flow in which the velocity flow at any given time, it does not change with respect to the space. Similarly, compressible and non-compressible. Compressible flow is one in which the density is not a constant, which means the density changes from point to point. So these are all the types of the flow. Now coming to the most important in fluid mechanics is the discharge. So discharge, also called as rate of flow. Normally, when we look at the pipe carrying liquids under pressure, we can also able to calculate what is discharge. Discharge is actually, that is the flow rate. That is the rate of flow. Means the known volume of water or any liquid flowing per every second. That is called flow rate. How we can calculate that flow rate? If the cross-sectional area of the pipe is known and the velocity, particularly average velocity of the fluid cross-section, the liquid through the cross-section is known, then we can find the discharge using the formula Q equals A into V. Now, a continuity equation. This is the most important in the fluid kinematics. So if you just look at the figure, so this is the direction of flow. I have taken two sections, 1 and 2. And these two, the section 1 and 2 are not uniform. The section was slightly smaller compared to section 2. Here we have, now, actually, it is based on the principle continuity equation, which is based on the equation principle of conservation of mass. So which says that, so the quantity of the fluid flowing through the pipe per second at all the cross section which remains same. That is called principle of conservation of mass. Then discharge at 1, which is equals to rho 1 into A1 into V1. So the discharge at 2, which is equals to rho 2 into A2 into V2. So where rho 1 and rho 2 are the densities at 1, A1 and A2 are the cross sections at 1, V1 and V2 are the velocities at 1. So now according to this law, they are always equal. So the moment when you equate, you will get this equation for incompressible. When it is compressible, the density will change. If the fluid is incompressible, the rho 1 means density at 1 and density at 2 will same. So then thereby finally you will get A1 into V1 equals 8, which means that This is called continuity, which means that the discharge value at any section will remain same. We use this formula in numerical problem or for the purpose of finding the velocity at any section. Now we have Bernoulli's equation. Bernoulli's equation, which is the modified form of Euler equations. So there are many devices which they are designed using this principle only. So Bernoulli's equation is nothing but the energy measuring equation. So using this equation, we can measure the energy in the flowing energy of the flowing liquid. So when liquid the flow takes place in a liquid with because fluid possesses certain amount of energy due to the energy that fluid has got, so it can travel inside the pipe. So here we have E square by 2, that is P by rho plus G into Z. It can also be written as V square by 2G, that is called kinetic energy, P by rho G, that is called pressure rate or pressure energy, that is Z. If you just divided by G, that equation changes to V square by 2G, P by rho G plus Z. That value is always constant. So this is called Bernoulli's equation, which gives energy at any point. So now there are assumptions. Before deriving the Bernoulli's equation. Even though fluid is not a ideal, we assume ideal. We assume steady. We assume incompressible. We assume the fluid is irrotational. Now, the application of Bernoulli's equation is used in the venturimeter design. It's just a venturimeter. So, if you want to measure the flow rate of a liquid moving in the pipe, we can fit a venturimeter to the pipe. So, venturimeter is always with the provision of a manometer. So, when we always fix the venturimeter at this is called inlet, the other one is called throat. The one end of the manometer we will fix at the inlet, the other one is some elsewhere in the throat. We fix this. Automatically it will start giving the manometer difference. Just if you record that, you no need to calculate the flow rate using any other technique. So when venturimeter is used, because venturimeter is always provided with the manometer, so just the manometer reading, within a fraction of a second you will get the flow rate. Similarly, Horifice meter. Like venturimeter, Horifice meter is another device which works on the same principle. So only the difference is venturimeter has got that three portion. There's a inlet, there's a converging portion, there's a throat portion. So whereas the Horifice meter, so it has got some Horifice plate. The water is made to flow through that Horifice plate, which has a small amount, a circular hole called Horifice. So just water, then that manometer is again fitted here, like in the venturimeter. We record the manometer reading, we can find the flow rate using Horifice meter. This is called pitot tube. This pitot tube, but using pitot tube, we cannot measure the flow rate. Instead, we can measure the velocity. Just pitot tube. So pitot tube is just a glass tube. It's a right angle bent glass tube. The one end is the lower end of the pitot tube is always directed to the flow. The other end is open above the atmosphere. The moment when the pitot tube is placed in a channel or a pipe, so the liquid will start entering and it keeps on rising. So using this, it looks like similar to your piezometer or the manometer. Now, with this background, we have a simple problem. A horizontal venturimeter. So you can see there is a problem on venturi. A horizontal venturimeter with inlet dia 20 and the throat dia 10 centimeter, which is used to measure the flow of water. The pressure at the inlet, because you know that venturi normally venturi manometer is connected, one at inlet of the venturi, the other one at the throat of the venturi. So the purpose is just to record the pressure at inlet and the throat. So if gauges are used, we record the pressure at throat and the inlet. When pressure is ready, we take the difference. When difference is ready, we can find H. When H is ready, we can find flow rate, like that. A horizontal venturimeter with inlet dia 20 and throat dia 10, which is used to measure the flow of water. The pressure at the inlet is 17,600 Newton per cm square, and the vacuum pressure at the throat. Actually, the pressure given at the inlet is 17,658 Newton per cm square, whereas the pressure at the throat is given as vacuum pressure, that is 30 centimeter of mercury. Calculate the discharge of water through the venturimeter. Take CD value as 0.98. So these are all the options. So how we can calculate? So let us calculate the dia of the inlet is 0.2 meter. 20 centimeter means 0.2 meter. Dia at the throat is 0.1 meter. So now CD value is given. So we can find the A1 and A2. They are the cross-section area at the inlet and the throat, respectively. Then pressure, when you know the pressure at inlet and the throat, the corresponding yet can be calculated. The pressure yet at inlet means, because the pressure at the inlet is 17,000, just P, if you divide by that by rho g, that value automatically called as yet. That value will become 80 meter of water. Similarly, the pressure value at the throat is given as yed directly, because the unit is centimeter. Centimeter means this is just in height. Yed means height. So 30 centimeter of mercury means it is not the pressure, instead it is a pressure rate. Instead it is a pressure rate. So 30, you just look at the unit 30 centimeter, that is that to vacuum, thereby it is minus 0.3 meter of mercury. Minus 0.30 centimeter of mercury or minus 0.3 meter of mercury. But since it is, we normally keep both the pressure rate in terms of the flowing liquid, which is water. So if you want to convert the pressure rate of the throat in the form of a water, you must multiply 13.6. So when you multiply, you will get 4.08, that, and both the pressure now kept in terms of meter of water. The difference of these two will be called as P1 by rho g minus P2 by rho g will be called as differential rate, denoted as H. So that value will become 22.08. So this value we will substitute in the discharge equation, that is CD into A1 into A2 root of 2GH divided by root of A1 square minus A2 square. When you substitute all this value carefully in this formula, you will get discharge in meter cube per second first. We always get the value in SI first. So when each meter cube equals 1000 liters. When you convert that into liters per second, you will get 165. Then you have the answer 165.55 LPS. That is the second answer, which is the correct answer. Now coming to another simple problem. A pipe through which water is flowing having a diameters 20 cm and 10 cm at the cross section 1 and 2 respectively. The velocity of water at suction 1 is 4 meter per second, 4 meters per second. Calculate the rate of discharge. There are four options again. Carrying water, the pipe having diameter 20 and 10 at the two cross section 1 and 2. By 1 and 10, cross section diameter different means it's a tapering pipe 1 and 2. The velocity of water at suction 1 is given as 4, and it is asked to calculate the flow rate. It is actually asked to calculate the flow rate. So if you want to calculate the flow rate at any suction, according to the law of continuity equation, the discharge at 1 and discharge at 2, they are one and the same. We can able to calculate the discharge value at any suction if you know just two values. The one value is its area. The other one value is velocity through it. Since luckily the cross section, because diameter of both the sections are known, we can find their area. And the velocity at the section 1 is known, we can also find V1. We can also find V1. Then if you multiply A1 V1, you will get the discharge. So if you just multiply just A1 V1, you will get the discharge. For curiosity, you can use continuity equation. You can find velocity at other section also. Then you can multiply A2 into V2 and then compare the velocity discharge found at 1, discharge found at 2, they are going to be same. You will get the discharge in cubic meter per SI unit. You every time for every parameter you will get cubic meter per second. And finally, when it is converted to liter per LPS, because each cubic meter will be equals to 1000 liters, then it will become 125.6. That's your first answer, is the correct answer. Now coming to flow through pipes. Flow through pipes is nothing but friction in pipes. So friction in pipes means it's some kind of a loss. Whenever the fluid which is flowing in a pipe, the fluid is always experiencing some resistance, due to which certain amount of energy the fluid is going to lose. So as far as losses are concerned, there are two types. One is called major loss, the other one is called minor loss. Major loss means the magnitude of the energy loss will be more. Minor loss means relatively they are very small compared to the major loss. So major loss is basically due to a friction, because when the flow takes place in a pipe, that tends to frict with the inner wall of the pipe, thereby there is a resistance, due to which the fluid is going to huge amount of energy. It's going to lose some energy. So that loss of energy, that is called major loss, which can be calculated using a very popular formula called Darcy-Weisbach equation, which says HF equals 4FLU square by 2GD. When this formula is used, HF means is a loss of it. F means is a friction factor. L means length of the pipe. V means velocity. V means volume, D means the diameter. In this formula, that letter F, that is called coefficient of friction, which can be calculated using the formula 16 by Reynolds, R means Reynolds number. If the Reynolds number is less than 2000, we can calculate F using this formula. Before we use this formula, it is advisable to calculate the Reynolds number. The Reynolds number basically it is rho v d by mu. For a we have to calculate Reynolds number. Reynolds number is a function of a flow that we have to calculate. Once the Reynolds number calculated and compared, when that comes less than 2000, then we use the formula 16 by R for F. Similarly, we also use 0.079 divided by R to the power 1 by 4. Actually, 1 by 4 is there. So a power of R is what? 0.25. 0.07 divided by R raised to the power 1 by 4, 0.25. This formula is used when the Reynolds number is more than 4,000 to 10 lakh. So this for either this we use or this we use. For turbulent flow, we use this second case. For very laminar flow, we use the upper case. So we also have one more formula, Chedis equation. So Chedis equation is particularly for the flow takes place in a channel, in an open channel, where V equals velocity, C is the Chedis constant, where M is the hydraulic mean depth, and the high is the bed slope, channel bed slope. Now coming to the minor losses. There are many types of minor losses. As far as pipe losses are concerned, there are various types of minor losses. If the pipe suddenly enlarges, there will be a loss. If the side suddenly contracts, there will be a loss. And at the entrance of the pipe, it will going to lose some energy. Suddenly, the exit of the pipe means outlet of the pipe, it will lose energy, which means that you have seen all this in the real field. So if the pipe out the outlet, it will lose some energy. If there is an obstruction to the pipe, it will lose energy due to the bend, because pipe will, when you lay the pipe, we need to bend the pipes many times energy. Also due to pipe fittings, just like a collar and so there are many types of pipe fittings due to which the pipe will going to lose some amount of energy. Now coming to the two important lines as far as the friction is concerned. There are two important lines of energy or hydraulic gradient line, total energy line. So we have to remember what is hydraulic gradient line and the hydraulic. Normally we measure if you wish to measure the pressure, the energy of the flowing liquid, there must be a reference called datum. So normally we keep the pipe center as a reference line. If you know the pressure at any section, if you know the velocity at any section, if you know the distance of the center from the datum, we can find the energy of any liquid in a pipe at any point. So hydraulic gradient line, if you know these energy, if the pipe kept horizontal, remember anywhere, then these two lines are always horizontal and parallel. These two lines are horizontal and parallel, but they are not superimposed, because total energy line is always more than the hydraulic gradient line. Hydraulic gradient line, as far as energy concerned, there are two types of energy. One is called pressure energy, the other one is called kinetic energy, the one more is called datum energy. So just in the hydraulic gradient line, it is the vertical height showing only two energy or two head. One is called pressure head, the other one is called datum head. So where a total energy line is the one, and which is the sum of all the three: pressure head, datum head, and kinetic head. So that is called total energy line. And friends, please remember, these two energy lines are always parallel. These two energy lines are always inclined and parallel. These two lines are parallel. But the reason for the parallel means the value of V, that as far as uniform cross-section pipe is concerned, the value of V, which remains same throughout the length, so that the constant amount of difference between these two energy will be V square by 2G. So that since V square by 2G, that particular term, which is not there in the hydraulic gradient line, so thereby, these two lines gets parallel, and using this concept, we can have some numerical problems. Then coming to flow through pipes, it's a compound pipe. You can see the pipe. So pipe consists is also called a pipes in series. You have pipes which has got you have three pipes. The diameter of each pipe D1, D2, D3, F1 and F2, F3 are the coefficient of friction in these pipe. L1, L2, and L3 are called the length of these two pipes. So we can build a pipe, or we can create a pipe which consisting of, or when the pipes are kept in series, they are called compound pipes. Now coming to equivalent pipe, the pipe of uniform the pipe of uniform diameter having loss of fade in the discharge equal to the loss of fade in the discharge of a compound pipe, and consisting of several pipes of different lengths and the diameter. And for as far as equivalent pipe is concerned, equivalent pipe is one which has got a diameter and which can be found using a Dupont equation. It's a very popular equation that is called Dupont equations. So using that we can find the equivalent pipe. So now with this, I would like to conclude my presentation. For any
Thank you very much for the presentation, sir. So, dear aspirants, here ends day 10, online training program for GATE 2021. So, please provide your valuable feedback by clicking the link that is provided in the comment section below. So, thank you very much for joining the sessions. Tomorrow, that is on day 11, GATE 2021 online training program, we'll be having again two sessions. One will be on transportation infrastructure and highway payments, and the second session will be on municipal solid waste. Both will be starting at the regular timings. That is, the first session will be starting at 2 p.m. and the second session would be starting at 3:45 p.m. So thank you very much. Keep watching.